Hello and, of course, welcome to the channel. Kettering University, formerly known as General Motors Institute of Technology, is a private non-profit university located in Flint, State, Michigan, USA, and offering degrees in Science, Technology, Engineering, and Mathematics (STEM), currently a fashionable acronym in English-speaking world. Every year it conducts a competition in mathematics for high school students grade 9 to 12, named Kettering Mathematics Olympiad, designed, as its webpage says, to identify and encourage with interest and abilities in mathematics. The time is usually 4 hours, no calculators or mobile phones are allowed. What I really like about the competition, it offers a list of past problems with solutions. So a student interested to participate can estimate the complexity of competition and properly prepare for it. And even if you are, like me, too old to participate, you may still find solving the problems challenging and quite often entertaining. The link to the list of problems and solutions will be given in the description under the video. Unfortunately, as you can see from the screenshot, the list has a glitch. Year 2011 is a dark spot, while year 2010 is really challenging. It has problems, but no solutions. That bothered me for quite a while, until I finally decided to fill the gap and present all solutions for this competition. And that's what this video is about. Just a few comments before you will have a chance to solve on your own. The first problem can be easily solved using determinants, however I am not sure that determinants are taught at US schools, so you should better avoid them. For the same reason, you should avoid using Fermat-Little theorem or Euler-Storshin theorem for the problem 4. However, while solving the problem, I expected the students to be familiar with the pigeonhole principle, known in some countries as principle of drawers, principle of boxes, or Dirichlet principle. By the way, number 49,367, as someone may have guessed, is a prime number. I wonder how the students were supposed to figure that out, given the time limit, no calculators, and no internet access. Fortunately, this isn't really essential. What really does matter, the number isn't divisible by 2 or by 5. Problem 2 should be easy for anyone familiar with trigonometry. Of course, any math competition should have an easy problem to ensure that there will be some winners. However, why there are 2 of them? Maybe because problem 1 was for year 9 and 10 students unfamiliar with trigonometry, while problem 2 was reserved for students year 11 and 12. For problem 3, I extensively use the well-known two-tangent lines theorem, which states that if 2 tangent lines to a circle are drawn from same point outside the circle, then the distances from the common point to the points of tangency are the same. The theorem actually has another part stating that the bisector of the angle between the line passes through the center of the circle. However, in the solution I am going to present here, this part isn't used. This approach is maybe not the only one, so you may come up with something much better. Problem number 5 has a much shorter solution than you may think. Just consider each line along with a triangle piece adjacent to it. In fact, each line has at least one adjacent triangle piece, while most of the lines actually have more than one. So you are certainly in much better position than the participants. The time is unlimited for you, and you can use a calculator if you wish. To be honest, I don't see a reason why a calculator should be disallowed at such level, given that the real math challenge is not about calculation, but about creativity, analytical mind, and deep knowledge of the subject. So please pause the video and try your best. Good luck! Problem number 1. Find the value of parameter a for which the following system of equations does not have solutions. The first equation is ax plus 2y equals 1. The second equation 2x plus ay equals 1. This is a system of linear equations for x and y, and I used the elimination method for solving it. In order to eliminate y, we multiply the first equation by a and the second equation by 2. And we get the equivalent system of linear equations then subtract the second equation from the first, and our goal is reached. Y is eliminated and we've got a linear equation for x. The right hand side is a minus 2 and the left hand side has a minus 2 as a factor. We just need to make it obvious by factorizing a squared minus 4 as a minus 2 times a plus 2. Now we see that if a equals 2, the equation for x turns into 0 times x equals 0, which is true for any value of x. Assuming x equals c, we can get the value of y from the first equation of the system, and the obtained values of x and y provide the solution of the system of equations with any value of c. This means infinite number of solutions, and we move on to the non-trivial case when a is different from 2. In this case, we can safely divide both sides of the equation for x by a minus 2, obtaining a simpler equation, which, however, still has a parameter in the coefficient for x. And again, the coefficient can be 0, and again we need to consider two cases. When a equals negative 2, the equation for x becomes 0 times x equals 1. Now the left hand side is 0 for any value of x, while the right hand side is 1 and can never equal to the left hand side. Therefore, there are no solutions in this case, and it's only remained to consider the case when a is neither 2 nor negative 2. In this case, x must be equal to 1 over a plus 2, while from the first equation of the system we get the only possible value for y, which also happens to be 1 over a plus 2. And this is the only available solution for the system. We need to find the value of a when the system of equations has no solutions. And we have found that this may happen only if a equals negative 2. So this is the answer. Problem number 2. Find all solutions of the equation cosine of 2x minus 3 times sine of x plus 1 equals 0. I wonder if cheat sheets were allowed at the competition. The web page says nothing about that. Anyway, I assume the contestants were smart enough to remember without cheat sheet that cosine of 2x equals cosine squared of x minus sine squared of x. Next we replace cosine squared of x with 1 minus sine squared of x and get 1 minus 2 sine squared of x. Alternatively, we could use sine of half angle identity. So we get sine squared of x equals 1 minus cosine of 2x over 2 and obtain exactly the same expression for cosine of 2x. Next we of course substitute the expression for cosine of 2x into the given equation, where 2 ones add up to 2, but since having a negative coefficient with the major term is not a good idea, the equation will be multiplied by negative 1. This gives a very pretty equation, having only sine of x in degree not exceeding 2, therefore the substitution t equals sine of x comes by itself. And we get a quadratic equation for t, whose discriminant is not just positive, it's even a full square. And we find the solutions, which are a half and negative 2. However, since t is actually the sine of x, it must be in the closed range between negative 1 and 1. Therefore, value minus 2 has to be disregarded, and we end up with the equation sine of x equals a half. The arcsine of a half is of course pi over 6, and since we are asked for all the solutions, this is actually redundant as all the solutions is always assumed unless otherwise specified. The answer is negative 1 to the power of k times pi over 6 plus pi k, where k is an integer. For someone who dislikes this sort of an answer, I give the alternative answer in two sets for x. So x is either pi over 6 plus 2 pi k, which can be rewritten as pi times 12k plus 1 over 6, or x equals 5 pi over 6 plus 2 pi k, which is pi times 12k plus 5 over 6, where of course k is an integer for both sets. Hopefully now everyone should be happy with the answer, and we can move on to a really challenging part of the assignment. Problem number 3. A circle of a radius r is inscribed into a triangle. Tangent lines to this circle parallel to the sides of the triangle cut out 3 smaller triangles. The radii, this is the correct plural of the word radius of Latin origin, even though someone may consider it old-fashioned, of the circles inscribed into these smaller triangles are equal to 1, 2, and 3. Find the value of r. In solving the problem, I used 2 common properties. They are so intuitive that in the competition I would actually go straight to the solution, taking them for granted. You can also skip the proofs by clicking the timestamp link below the video. For someone who didn't, here are the 2 statements. Statement A is already mentioned, 2 tangent lines theorem. If 2 tangent lines are drawn to a circle from same point outside the circle, in fact the last phrase is redundant, the segments from the common point to each point of tangency have same length. In other words, these segments are congruent or equal, whatever term you prefer to use. This is actually a textbook theorem, but the proof is so simple that it wouldn't take much time to discuss it here. So we have a circle with center at point O and point A outside the circle. 2 tangent lines to the circle are drawn from point A with the points of tangency B and C, and it is claimed the segments AB and AC have same length. To prove that, we connect point O with points A, B, and C, and since the tangent line is always perpendicular to the radius at the point of tangency, we get 2 right angles, angle ABO and angle ACO, forming 2 right-angled triangles, triangle AOB and triangle AOC. These triangles have a common hypotenuse AO and equal legs OB and OC as radii of same circle. Therefore, the triangles are equal to each other, so the other legs of each triangle, AB and AC, are equal to each other, which is what the claim was about. Also, the triangles have equal acute angles, BAO and CAO, which means that AO is the bisector of angle BAC. Statement A is proven, and now to statement B. In similar triangles, the ratio of in radii, the last word standing for the radii of inscribed circles, is equal to the ratio of semi-perimeters, or half perimeters for someone confused with the Latin prefix. The proof presented here is certainly not the shortest, however it's simple. So, given triangle ABC and triangle A'B', C' similar to triangle ABC. Sides BC, AC and AB have lengths A, B and C respectively. In the similar way, we use letters A', B' and C' for the sides of triangle A'B', C'. Let S be the semi-perimeter of triangle ABC. Then 2S is the full perimeter and equals A plus B plus C. Then we have S', the semi-perimeter of triangle A'B', C', and the value of 2S' equals A' plus B' plus C'. Then R and R' are the in radii of triangles ABC and A'B', C' respectively. Also O and O' are the centers of inscribed circles, the incenters of triangles ABC and A'B', C' respectively. It is well known, and it actually falls for the 2 tangent line theorem, that the incenters are the points where the bisectors meet. Since a side of a triangle is tangent to the inscribed circle, each radius to a tangent point is perpendicular to the corresponding side. Sorry for such a long introduction, but finally we move on to the proof. From the similarity of triangles, it follows that angle B equals angle B' and angle C equals angle C'. The value of angle OBC is half the value of angle B, and the value of angle O'B', C' is half the value of angle B'. Therefore, angle OBC is equal to angle O prime B prime C prime. In the similar way, angle OCB equals angle O prime C prime B prime. Consequently, triangle BOC is similar to triangle B prime O prime C prime by angle-angle rule, while in similar triangles, the sides are proportional to the altitudes. For the sides, we have A and A prime, while the altitudes of triangles BOC and B prime O prime C prime are just the in radii R and R prime. So we got a proportion A over A prime equals R over R prime. Exchanging the middle terms of the proportion gives A over R equals A prime over R prime. In a similar way, from triangles AOC and AO prime C prime, we get B over R equals B prime over R prime. And from triangles AOB and A prime O prime B prime, C over R equals C prime over R prime. And we add the last three equalities, then replace A plus B plus C with 2S, and A prime plus B prime plus C prime with 2S prime. Then we divide by 2, and again swap the middle terms. That's what we needed, and that's what we obtained. Now to the actual task. Given triangle ABC, having semi-perimeter S and in radius R. Let E, F, and G be the points of tangency of the incircle with segments BC, AC, and AB respectively. According to the two tangent lines theorem, segments AF and AG have same length, and let P sub A be their common length. In a similar way, the length of segment BG equals the length of segment BE equals P sub B, and the length of segment CE equals the length of segment CF equals P sub C. Then we write that the perimeter of triangle ABC, which is 2S, equals the length of AB plus the length of BC plus the length of AC. However, the length of segment AB is P sub A plus P sub B. The length of segment BC is P sub B plus P sub C. And the length of segment AC is P sub C plus P sub A. After distributing and reducing the common terms, we get 2S equals 2 times PA plus 2 times PB plus 2 times PC. Therefore, S equals just P sub A plus P sub B plus P sub C. Now let's draw a line parallel to side BC and tangent to the incircle at point P. Let L and K be the points where the parallel line meets sides AC and AB respectively. So we can write that KL is parallel to BC. And again we can apply the two tangent lines theorem to point out that the length of segment KP equals the length of segment KG, and the length of segment LP equals the length of segment LF. Now consider triangle AKL. Using S sub A for the semi-perimeter of triangle AKL, we can write 2 times S sub A equals the length of AK plus the length of KL plus the length of AL. Then the length of KL can be represented as the length of KP plus the length of LP. Now the sum has 4 terms. Nevertheless, it is more appropriate for the simplification. Indeed, using the previously obtained equalities, we can replace the length of KP with the length of KG, and the length of LP with the length of LF. Next, we can see that the segments AK and KG form together segment AG with the length P sub A, while segments AL and LF form segment AF with the length also equal to P sub A. So 2 times S sub A happens to be equal to 2 times p sub a. Therefore, the semi-perimeter of triangle AKL is just p sub a. We are getting close to using statement B, for which we need two similar triangles. And you have certainly guessed which triangles we are going to use. Indeed, since KL is parallel to BC, we have two pairs of corresponding angles. Angle AKL equals angle ABC, and angle ALK equals angle ACB. Therefore, triangle AKL is similar to triangle ABC by angle-angle rule, and applying statement B to these triangles gives R sub A over R equals S sub A over S, where R sub A is of course the inner radius of triangle AKL. Replacing S sub A by P sub A, we get R sub A over R equals P sub A over S. And again, you probably can guess what is going to be next. We draw a line MN parallel to line AC and get triangle BMN with inner radius R sub B. Triangle BMN is also similar to triangle ABC, so we can write the equality for R sub B. Yet another triangle is needed to make the drawing looking really great. Triangle CPQ, where of course PQ is parallel to AB, and we need a name for the inner radius. I'll take R sub C, as I really like the sound of it. The equality for R sub C completes the nice group of three equalities, and in order to make them really united, we need to add them up. Can we simplify this equality? Of course we can, given that the numerator in the right hand side is just S. This equality was waiting for a long time for its turn, and this is its golden moment. The right hand side is just 1, and so must be the left hand side. This means that the inner radius of the whole triangle is the sum of the inner radii of the smaller triangles. But the inner radii of the smaller triangles are given. They are 1, 2, and 3. So we only need to add them up. 1 plus 2 plus 3, where's my calculator? Dum. It's 6. Let me double check. That's right, the answer is 6. A beautiful problem and a beautiful result. Problem number 4. Does there exist an integer k such that log base 10 of 1 plus 49,367 times k is also an integer? Probably the shortest condition of all, and the first problem not requiring a numeric answer. To be or not to be? This is the question. I expect the answer to be positive, and it really is. Indeed, if k equals 0, the expression is reduced to the logarithm of 1, which is of course 0, which is of course an integer. So the problem is solved and we can move on, but we won't. Because firstly, we are looking for a challenge. Secondly, this is not what the authors of the problem meant. What the problem meant were the positive values of k, and this is what will be assumed further on. So k is a positive integer, the logarithmic expression, name it n, must be just an integer. However, for a positive k, the value under the logarithm is more than 1. Therefore n must be also a positive integer. Despite all my respect to a decimal logarithm, in this case I have a strong desire to get rid of it. So, with your tacit permission, I will apply the exponential function base 10 to both parts of the equation. The right-hand side of the equation may scare someone. However, we know very well that this is just the expression under the logarithm. The obtained equation looks much better because it can be solved for k. Since both k and n are undefined, nothing stops us from paraphrasing the question in the opposite way. So we come up with the equivalent question. Is there a positive integer n such that 10 to the power of n minus 1 or divided by 49,367 is also an integer? And this is actually the question we are going to answer. A straightforward answer to that is given by Euler's Toshin theorem. Moreover, since 49,367 is a prime number, we can simply apply Fermat's little theorem. However, we agreed to be unfamiliar with either of the theorems. We are even assumed to be unaware that 49,367 is a prime number. However, something about this number is quite obvious. Firstly, it is an odd number. Secondly, it is not divisible by 5. In other words, the greatest common divisor of numbers 10 and 49,367 is 1. The numbers with greatest common divisor equal to 1 are called coprime numbers. Quite obviously, the numbers are coprime if and only if they have no common prime factors. In order to stop dealing with such an awkward number as 49,367, let's replace it with letter B. Furthermore, we can avoid dealing with any specific number by replacing number 10 with letter A. Our objective is to prove the following statement. If positive integers a and b are coprime, there exists a positive integer n such that a to the power of n minus 1 or divided by b is an integer. And of course, proving the statement means giving positive answer to the question. As it was mentioned before, we are going to use the pigeonhole principle. Consider b plus 1 numbers, a to the power of 0, a to the power of 1, etc. up to a to the power of b. Let r sub n be the remainder of dividing a to the power of n by b. So we get b plus 1 remainders, r sub 0, r sub 1, etc. up to r sub b. Value of remainder is always a non-negative integer strictly less than the divisor. Therefore, there are only b possible values of the remainder from 0 up to b minus 1. According to the pigeonhole principle, b plus 1 remainders with b possible values should have at least 2 equal remainders. In other words, there are 2 different indices I and j, so that r sub I equals r sub j. And let I be the greatest of the indices. I is greater than j. Since a to the power of I and a to the power of j have same remainder when divided by b, their difference must be divisible by b. In the difference, we can factor out a to the power of j. Quite obviously, a to the power of j has same prime factors as a, only their power is j times bigger. Since a and b are coprime, they have no common prime factors. Then a to the power of j and b have no common prime factors either. This means that a to the power of j and b are coprime. Here comes a well-known property of coprime numbers that I expect to be familiar to high school students. If the product s times t is divisible by u, while one of the factors is coprime with the divisor, then another factor must be divisible by divisor u. The strict proof is a bit complex, but the reason is quite simply to understand. If st is divisible by u, while s and u have no common prime factors, then all prime factors of u must appear in t in sufficient power, meaning that t is divisible by u. Applying the property to the difference a to the power of I and a to the power of j, we see that the whole difference is divisible by b, while the first factor a to the power of j is coprime with b. So we conclude that the second factor, which is a to the power of I minus j or reduced by 1, is divisible by b. This means that if n equals I minus j, then the value of a to the power of n minus 1 or divided by b, name it k, is an integer. Since I and j are integers and I is greater than j, n is a positive integer. Then the formula for k shows that k is also a positive integer. The statement is proven and the problem is solved. Just a short remark. According to Fermat's little theorem, for a equals 10 and b equals 49,367, n equals 49,366, while k is quite a big number, containing 49,362 digits in decimal representation. Problem number 5. A plane is divided by 3015 straight lines such that neither two of them are parallel and neither three of them intersect at one point. Prove that among the pieces of the plane obtained as the result of such division, there are at least 2010 triangular pieces. First of all, let's all together congratulate this problem with its semi-centennial anniversary. That's right, the problem was presented for the first time back in 1972 at Moscow City Mathematical Olympiad. And I don't mean Moscow State, Idaho, but Moscow, the capital of the former Soviet Union. The country is dead for over 30 years, but the problems originated there, like friendly ghosts, appear all the time at any parts of the world. But I don't care, as I am not the copyright owner. Also, for this competition, the problem was updated. While there were originally 3000 lines and 2000 pieces, now we see 2010 pieces, probably to match the year of competition. And the number of lines has been increased accordingly. So, someone may argue that this is a different problem. To a certain extent, this problem is even simpler than the previous ones, as it doesn't require a good knowledge of maths. Just common sense will do. So let's apply common sense. Take n to be the number of lines. Since there are no parallel lines, each line intersects all n-1 other lines. And the intersection points must be distinct. Otherwise, we would have more than two lines passing through a single point, which is disallowed. This means that each line contains exactly n-1 intersection points. So, in order to compute the total number of intersection points, we multiply the number of lines by the number of intersection points at each line, and since each intersection point belongs to two lines, it is counted twice. Therefore, we need to divide the result by 2. So we get n times n-1 divided by 2, which is in fact the number of combinations of n elements by 2. To find the number of intersection points outside a line, we can either subtract n-1 from the total number of intersection points, or just say that n-1 other lines meet at n-1 times n-2 divided by 2 intersection points. Also, from the conditions of the problem, it follows that any three lines form a triangle. Therefore, the total number of triangles is the number of combinations of n elements by 3. However, not any triangle is a triangular piece, as a line can split it into smaller pieces, while we are looking for unsplit triangular pieces. We can find the total number of unsplit pieces using the fact that n-1 intersection points on a line split it into n parts. For example, if n equals 4, we have 3 intersection points and 4 parts. Among these n parts, 2 edged parts are unbounded and have infinite length. The remaining 2 parts are bounded and have finite length. And of course, the bounded parts exist only if n is no less than 3. Now we can compute the number of bounded pieces, b sub n. When the number of lines is less than 3, there are no bounded pieces. So b sub 0, b sub 1, and b sub 2 are all equal to 0. For 3 lines we have 1 bounded piece. Next, the fourth line contains 2 bounded parts, producing 2 new bounded pieces, while 2 other new pieces are unbounded. So the number of bounded pieces is increased by 2. Then line 5 brings 3 new bounded pieces and 2 new unbounded pieces. And so on, until we draw line number n, bringing n-2 new bounded pieces. Therefore, if n is 3 or more, the number of bounded pieces is the sum of first n-2 positive integers, which is equal to n-1 times n-2 divided by 2. The number of unbounded pieces u sub n is easier to evaluate, as each new cut brings 2 unbounded pieces. However, the very first cut brings only 1 new piece, as before the cutting starts, the whole plane already represents 1 unbounded piece. Therefore, u sub 0 equals 1, and u sub n equals 2 times n for a positive n. Hence, the total number of pieces, p sub n, can be found by adding up b sub n and u sub n. There is also a straightforward way to count the total number of pieces. The result is n squared plus n plus 2o divided by 2, which can also be written as n times n plus 1o divided by 2 plus 1. In particular, 3015 lines give over 4.5 million bounded pieces, which is much more than 2010. The reason is, of course, that the problem asks for triangular pieces only, which isn't so easy to count. However, the question is not about the exact amount of pieces, but about the lower margin of it. Now we can wipe out most of the page containing the irrelevant stuff. However, I hope you don't regret much about that. Firstly, because it may give you a hint to another problem. Secondly, that helped you to emerge into the problem, to get a feeling of it. This line I left for purpose. It shows that if n is 3 or more, the number of intersection points outside each line is more than 0. So we come to statement 1. If n is no less than 3, there exist intersection points outside each line. Statement 1 looks pretty obvious, however, it will be helpful for proving a less obvious statement. Number 2. If n is no less than 3, each line has an unsplit triangular piece adjacent to it. Where adjacent piece to a line, as you've probably guessed, means a piece with its side along the line. In other words, with 2 vertices belonging to the line. So let's take any line and name it L. According to statement 1, there are intersection points outside the line. Let A be the intersection point outside line L having the shortest distance to L. If there are several points having the shortest distance, we of course take any of those. According to the conditions, point A belongs to 2 and only 2 lines, forming with line L triangle ABC. Since vertices B and C belong to line L, triangle ABC is adjacent to line L, and we only need to prove that it is unsplit. Suppose there is a line splitting the triangle ABC. Since according to the conditions, such a line cannot pass through any vertex of triangle ABC, it must intersect 2 sides of the triangle, and at least one of the intersected sides will be different from side BC. It can be either side AB or side AC. Let's for certainty assume that the line crosses side AB and name D the intersection point. It looks quite obvious that point D is closer to line L than point A, However, for some skeptical people that may happen to be among the viewers, I'm going to give a strict proof of that. So let A' and D' be the projections of points A and D respectively to line L. We get two right-angled triangles BAA' and BDD'. The triangles have common angle B, therefore they are similar, and we can write that the ratio of legs DD' and AA' equals the ratio of their hypotenuses DB and AB. However, since point D is within the segment AB, the length of segment DB is less than the length of segment AB. This means that the ratio of the hypotenuses DB and AB is less than 1. Therefore, the ratio of legs DD' and AA' is also less than 1. Therefore, the length of DD' is less than the length of AA', which means that point D has a shorter distance to L than point A, which is of course a contradiction with the choice of point A. Statement 2 is proven. So let T sub n be the number of triangular pieces formed by n lines. It has been already proven that each line has at least one adjacent triangular piece. However, each triangle has 3 lines surrounding it, so up to 3 lines may have it as the adjacent triangular piece. This suggests that for the lower margin of T sub n, the number of lines has to be divided by 3. So we have T sub n is no less than n divided by 3, and since T sub n must be an integer, we can round this number up to an integer. In other words, we should take ceiling function of n divided by 3, where ceiling of a number, for someone who may be unaware, is the lowest integer which is not less than the number. For 3015 lines, this number of lines is divisible by 3, so ceiling function in this case is redundant. The lower margin is 1005, while what we need is twice as much as that. Somehow we need to find another adjacent triangular piece for each line. But hold on, each line actually has 2 sides, side 1 and side 2. What if we take intersection points located only at side 1 and find the adjacent triangular piece there? Then in the similar way we find the adjacent triangular piece on side 2. No, that won't work, because we cannot be certain that there will be intersection points on both sides. What is the most painful here? There is a strong feeling that lines having all intersection points on one side do exist, as each drawing has an edge. Let's call such a line an edge line. In fact, very few amount of edge lines may be alright, as long as the ceiling function rounds the margin up to the value we need. Let's find out how many edge lines we can afford. Let m be the number of edge lines with at least one adjacent triangular piece. The remaining n minus m lines will have at least 2 adjacent triangular pieces each. This gives 2 times n minus m plus m pieces, which is simplified to 2n minus m. Then we have to divide this number by 3 and take the ceiling of it. For n equals 3015, the lower margin is the ceiling of 2010 minus m over 3. Therefore, in order to get 2010 as the value of ceiling function, m must be less than 3. In other words, we can be completely happy if there are no more than 2 edge lines. Let's find out if this is really the case. Take 3 lines. 3 lines mean 3 intersection points. Therefore, each line has only one intersection point outside it. This means that any one of these 3 lines is an edge line. 3 edge lines, while we are allowed to have no more than 2. Let's see what we have with 4 lines. BC is an edge line, AC is another edge line, and no more. Maybe indeed, starting with n equals 4, everything goes in our favor. See if we can prove statement number 3. If n is no less than 4, there are no more than 2 edge lines. Suppose n is no less than 4, but nevertheless there are at least 3 edge lines. Here are 3 edge lines, which I deliberately colored orange to differentiate from non-edge lines. Since the number of lines is more than 3, there should be another line, which isn't necessarily an edge line. However, it must intersect all 3 edge lines on the drawing in 3 distinct points. One of these 3 points, point E on the drawing, will be between 2 others. This intermediate point belongs to a certain edge line, line AB on the drawing. This edge line, according to the definition, must have all intersection points on one side of it. However, points D and F are located on different sides of line AB. Hooray! The statement 3 is proven, and we have a better margin for T sub n. T sub n is no less than the ceiling of 2n minus 2 over 3. It applies only to n no less than 4. However, we are not after such a miserable amount of lines. Our target is 3015 lines. What will be the margin for this amount? It is the ceiling of 6028 thirds, which is the ceiling of 2009 and 1/3, which is 2010, just what we need. The problem is solved. However, the estimation obtained here is very rough, especially for such a big number as 3015, where the minimum number of pieces is in fact much higher. The accurate estimation was found in 1979 by 2 US mathematicians Branko Grunbaum and G.C. Shepherd. Now we know that the number of unsplit triangular pieces for n lines where neither 2 lines are parallel and neither 3 of them share a point is no less than, I really can't believe it, n minus 2. This estimation of course covers the case of 3 lines as well, and as I've already mentioned, it is accurate, meaning that for any n no less than 3, there exists a set of n lines giving exactly n minus 2 triangular pieces. In particular, for 3015 lines, there will be no less than 3013 triangular pieces. So Kettering University can present the problem again for the Math Olympiad in the year 3013. The number of pieces will be of course 3013, while the number of lines will still be 3015. By then, the contestants will surely be able to solve such a problem. What really worries me, will the calculators be allowed at that time? But now the time has come to the end.